Something is happening in the quiet darkness beyond the planets. An object from another star system has entered our neighborhood, and what the James Webb Space Telescope just found about it is rewriting everything we thought we knew about how the universe builds its worlds. The object is called 3I/Atlas. Officially, it's classified as the third known interstellar visitor ever detected after Oumuamua in 2017 and 2I/Borisov in 2019. But what Webb has revealed about its composition is so bizarre that even the scientists who confirmed the data admit it shouldn't exist. When astronomers first detected 3I/Atlas, it didn't look like anything unusual. Another faint point of light, another traveler passing through the solar system. But as observatories across the world began gathering data, one anomaly after another began stacking up. Its orbital path was too steep, its tail was behaving erratically, and its surface reflectivity hinted at something chemically alien. So NASA turned one of its most powerful eyes toward it, the James Webb Space Telescope, parked nearly 1,000,000 miles from Earth. Webb's infrared instruments are designed to decode light into chemical fingerprints, revealing exactly what an object is made of. What they found inside the coma of 3I/Atlas sent shockwaves through the astronomy community. Instead of the familiar signature of water vapor, the frozen breath of ordinary comets, Webb detected something else: carbon dioxide. A lot of it. Over 80% of the volatile material escaping from the object appeared to be pure CO2 gas, mixed with a smaller fraction of carbon monoxide and only traces of water. This is the exact opposite of what we expect from any comet, whether local or interstellar. Comets are supposed to be dirty snowballs, mostly frozen water, sprinkled with dust and organic compound. But 3I/Atlas looked like something else entirely, a kind of dry chemical engine, leaking exhaust that resembled industrial emissions more than natural ice evaporation. Scientists immediately tried to find a natural explanation. Perhaps the object had formed in a colder region of its parent system, where carbon-based ices could dominate. But that theory quickly began to fall apart when the data showed that its surface temperature didn't match such a composition. It was too warm, implying that the CO2 was not just frozen gas sublimating from its surface, but possibly being released from deeper layers through an unknown mechanism, one that didn't fit the known physics of comet activity. The James Webb team at the Space Telescope Science Institute described the finding as unexpected and unprecedented. In quiet tones, a few even called it unnatural. The mystery deepened when Webb captured faint spectral lines that hinted at metallic compounds beneath the outer shell. Traces of nickel and magnesium were detected, but without the iron that normally appears alongside them in natural space rock. This imbalance was strange. Every meteorite, every asteroid, every comet we've ever studied has a predictable mix of heavy elements forged in ancient supernova. Yet 3I/Atlas seemed chemically edited, as if some process had stripped it of iron entirely. Some researchers suggested this could happen through extreme heating or magnetic differentiation inside a forming system, but no one could explain how such material could survive ejection into interstellar space and still remain this pure. By late September, data from the Nordic Optical Telescope and the Webb infrared spectrograph were being compared in real time. Both confirmed the same thing. 3I/Atlas is unlike any interstellar visitor we've seen before. Oumuamua, the first, was small, silent, and strangely accelerated by a non-gravitational force that Avi Loeb at Harvard famously suggested could be artificial. 2I/Borisov looked more like a normal comet with a trail of dust and ice. But 3I/Atlas, this new arrival, seems to be something in between, too structured to be random, too reactive to be natural. The more data Webb collects, the more it defies every model we use to explain how comets behave. Somewhere around early October, Webb's MIRI instrument captured a heat map that made scientists pause. The thermal emission wasn't uniform. There were concentrated regions along the nucleus that flared in a repeating pattern, almost like heat signatures pulsing at intervals. Such thermal variability has never been recorded in a comet before. One astronomer from ESA described it quietly during a closed meeting as anomalous energy cycling. In simpler terms, it's as if 3I/Atlas was doing something, not just reacting to sunlight, but regulating its own temperature in a way no natural body should be able to do. At first, this was dismissed as a calibration issue. Infrared detectors are notoriously sensitive, and even a small error in wavelength calibration can mimic strange reading. But after 3 independent teams verified the data using different instruments, including NASA's Infrared Telescope facility in Hawaii. The pattern remained. 3I/Atlas wasn't behaving randomly. It was emitting bursts of heat and gas that followed a rhythm, a cycle of roughly 11 hours. The question was why? Back on Earth, theoretical astrophysicists began running simulations. Some proposed that rapid rotation could explain the repeating outgassing, like jets venting from spinning nozzles as the object turned. But the rotation speed required for that would tear most comets apart. Others pointed out that the composition itself might allow for controlled degassing, a kind of natural venting pattern caused by layered ices. But again, the ratio of carbon dioxide to water made that nearly impossible. The mystery only deepened. What Webb confirmed next made the debate explode. Within the chemical data were spectral signatures of complex hydrocarbons, long carbon chains that formed the building blocks of life. Not just methane or ethane, but heavier molecules like acetylene and benzene, substances that can only form under specific chemical conditions. These compounds are not rare in the cosmos, but their abundance here was off the chart. And more importantly, they appeared to be organized in a pattern across the object's surface. Webb's mapping tools showed regions rich in these hydrocarbons alternating with zones dominated by CO2, almost like a repeating grid. No natural comet ever shows chemical zoning like that. They're messy, chaotic, mixed by billions of years of impacts and solar heating. But 3I/Atlas seemed patterned, engineered by temperature, density, or something else. One scientist compared it to the difference between a broken rock and a carved sculpture, and then came the most unsettling data of all. During its closest observation window, when the object moved just beyond the sun's glare, Webb picked up faint electromagnetic fluctuation, microbursts in the radio range, synchronized with the same 11-hour thermal pulses. They were too weak to be called signal and too irregular to match known astrophysical sources. Yet, their periodic nature raised an unspoken question. Could 3I/Atlas be emitting? No one is calling it proof. No one is saying it's artificial. But the official reports, now circulating quietly through NASA and ESA channels, use careful phrases like non-random modulation and complex periodicity, the kind of language scientists use when they don't yet understand what they've found, but can't ignore it either. Whatever 3I/Atlas is, it's not just another rock from the star. The James Webb Telescope has revealed a chemistry that defies formation model, a heat pattern that defies physics, and a behavior that defies chance. And this is just the beginning. By mid-October, the international astronomy community was no longer treating 3I/Atlas as just another interstellar curiosity. Behind closed doors, teams from NASA, ESA, and JAXA had begun to share encrypted data streams through private scientific networks, comparing notes about what Webb sensors were seeing. The official narrative was that it was all routine collaboration, but those who have worked in these circles long enough could tell something was different this time. Meetings were being held without the usual public releases. Research papers were delayed for verification, and the words restricted dataset began to quietly appear on internal memos. It wasn't just the composition anymore, it was the movement. When Webb's positional tracking data came in from its mid-infrared instrument, astronomers noticed a subtle irregularity in the object's trajectory, an oscillation too small to classify as a full course change, but too precise to be a random tumble. Normally, comets that vent gas experience what's called outgassing acceleration, unpredictable tiny shifts in speed and direction caused by jets of evaporating ice. But 3I/Atlas was showing a consistency that made no sense. The adjustments were periodic, almost deliberate, as if the object were correcting itself to stay on a specific path. This was the same phenomenon that had baffled scientists with Oumuamua years earlier, when its motion changed slightly without any visible jets. But this time, Webb's hypersensitive instruments were watching every fluctuation, and what they saw was coordinated. Once every 11 hours, matching the thermal pulses already detected, 3I/Atlas seemed to release a faint burst of gas in one direction, then realign itself. The direction wasn't random either. Each emission seemed oriented toward the plane of the solar system, almost like a navigation maneuver. For the first time, the possibility of an engineered behavior was whispered, though never on record. Scientists don't like using words like control or self-correction. They prefer phrases like anomalous vector consistency or repeatable non-gravitational acceleration. But everyone knew what it implied. And yet, Even with all this data, there was still a layer of secrecy. Astronomers from the Planetary Defense Coordination Office confirmed that telescopes worldwide had been redirected toward 3I/Atlas, but the results of those observations weren't being made public. The James Webb mission logs show several hours of unannounced observation time, all aimed at a single target, yet no images or spectra were uploaded to NASA's open archive. This was not standard protocol. Rumors began circulating among researchers that something in the spectral data had been flagged as sensitive. A few insiders hinted that the material reflectivity of 3I/Atlas's surface didn't match any natural mineral signatures known in our catalog. Instead, it showed a flat metallic reflectance curve, the kind of response you'd expect from a manufactured alloy rather than frozen dust. The signal wasn't strong enough to make any definitive claim, but strong enough to trigger a review by NASA's Materials Spectroscopy Group. One of the few scientists willing to speak publicly was Professor Avi Loeb, who had already made headlines years earlier suggesting that Oumuamua might have been an artificial probe. He called the new data on 3I/Atlas highly significant, noting that the combination of carbon-dominated chemistry, non-gravitational motion, and anomalous thermal cycles placed it in a class of its own. He pointed out that if such an object were designed rather than formed, its carbon dioxide emissions could be a byproduct of some internal energy system rather than simple sublimation. In other words, what we were seeing might not be a comet tail at all, but exhaust. The suggestion was controversial, even heretical, but it spread fast. Cosmic coincidences don't repeat themselves easily, and now humanity had seen 3 interstellar objects in less than a decade, each stranger than the last, each closer to the idea that maybe we're not just watching random debris, but technology from somewhere else. By the end of October, Webb had gathered enough data to produce a detailed chemical map of 3I/Atlas's surface. It showed a patchwork of zones rich in hydrocarbons, alternating with high-density carbon dioxide deposits. The patterns were too geometric to ignore. The divisions between regions were sharp, straight, and evenly spaced. Some astronomers described them as panel-like, as if the surface were divided into segments that heated and cooled in sequence. That patterning corresponded exactly with the infrared flares detected earlier. The objects seemed to be covered in some kind of layered material that responded to sunlight and cycle, absorbing and releasing energy in precise intervals. As 3I/Atlas moved closer to the sun, the activity intensified. Webb recorded a spike in its brightness that didn't match the expected energy curve. Normally, when comets approach perihelion, they brighten smoothly as the ice vaporizes. But this time, the brightness increased in sharp, measurable steps, bursts separated by about 11 hours, the same cycle repeating again and again. That rhythm began to look less like natural sublimation and more like timed activity. Astronomers from the Max Planck Institute cross-checked the timing with solar wind data from the Parker Solar Probe. The results were startling. Each flare from 3I/Atlas coincided with a small dip in solar particle density, as if the object's emissions were somehow influencing the space environment around it, pushing the solar wind back or interacting with it in an unknown way. That kind of influence would require an active magnetic field or electromagnetic output, neither of which should be possible for a simple comet nucleus. Meanwhile, amateur astronomers tracking the object's visible light curve noticed something else. The color of its tail was changing. Early images showed a pale bluish glow, typical of ionized gases, but as weeks passed, the tail began to take on a reddish hue, similar to emission from carbon compounds under heat stress. The shift was gradual but undeniable. Spectroscopy from ground-based telescopes confirmed the color change corresponded to increasing carbon chain length, as if the material leaving the surface was chemically evolving over time. This suggested complex reactions were taking place inside the object as it absorbed solar energy, reactions we've never seen in any natural comet. Then came the audio, not literal sound, but radio emissions converted into audible frequencies by researchers at the SETI Institute. The James Webb Telescope doesn't pick up radio directly, but supporting observations from NASA's Deep Space Network did, and within those data were faint rhythmic fluctuations that, when translated into sound, produced a strange mechanical hum. Scientists described it as a pulsed broadband pattern, repeating every few seconds within a broader 11-hour modulation cycle, the same pattern seen in the heat and gas emission. For those who listened to the playback, it didn't sound like noise, it sounded deliberate. Still, the official statements remain cautious. NASA describes the emissions as a novel interaction between solar radiation and carbon-dominated volatiles, avoiding any suggestion of technology. But privately, Researchers admit there's no consensus. Every natural explanation requires conditions so specific, so unlikely, that they border on impossible. It's as if nature has built something that mimics machinery. And yet, in the middle of all the uncertainty, something else is becoming clear. This object is teaching us that interstellar chemistry might be far more diverse than we imagine. It's possible that 3I/Atlas formed in a system rich in carbon dioxide ice, where water was scarce, or in an environment where supernova debris created exotic mixtures of elements. But even if that's true, the level of structure and control it exhibits remains beyond any natural precedent. The James Webb team is still analyzing terabytes of data, searching for patterns that might explain it all. But so far, every answer opens a new question. What kind of process could create such material organization? What kind of environment could strip a body of iron but leave nickel intact? And most disturbingly, why does every measurable cycle repeat with such mechanical precision? The next observation window is approaching. 3I/Atlas is moving behind the sun into a region we can't directly observe. When it re-emerges weeks from now, the world may see whether its course has changed again, whether it's truly just drifting through or adjusting for something else. The silence from the agencies suggests they already have clues. As the calendar turned and 3I/Atlas slipped behind the sun, telescopes all across the world went blind to it. The object had entered a region of sky too close to the solar glare for any optical instruments to see. For weeks, there was silence. No updates, no data, no images. It was as if the object had disappeared completely. But in the background, deep space monitoring stations still tried to listen. Radio antennas in Canberra, Madrid, and Goldstone stayed trained toward the coordinates where 3I/Atlas should have been, scanning for any sign of reflected signals or emission spikes. Then, quietly, one of those antennas picked up a faint signal. It wasn't a transmission, not in any artificial sense, but a reflected pulse, something that shouldn't have been strong enough to detect at all. The reflected intensity suggested a surface far smoother and more reflective than any known comet nucleus. Most comets scatter incoming radio waves chaotically, producing diffuse echoes. But the return from 3I/Atlas came back narrow and coherent, almost mirror-like. Engineers described it as specular reflection, the kind you'd get from a metallic surface rather than porous ice or dust. It was so unusual that they double-checked the calibration 3 times, certain it was an instrument error, but every system was working perfectly. When 3I/Atlas finally emerged from behind the sun, Webb and a dozen ground-based observatories immediately locked onto it again. What they saw stunned everyone. The object was brighter, nearly 3 times brighter than before its solar conjunction. Comets typically lose mass as they pass near the sun, fading afterward as their volatiles burn away. But 3I/Atlas had grown more reflective, as if something on its surface had been renewed or reactivated. The first spectral scans after re-emergence revealed new features. Traces of metallic magnesium and silicon appeared in the emissions, elements not previously detected in its composition. The thermal cycles had shifted too. Instead of the 11-hour rhythm, Webb recorded a new pattern closer to 9.5 hours, meaning the internal dynamics had changed. But that wasn't the most disturbing discovery. As 3I/Atlas moved away from the sun, its path diverged slightly from the expected gravitational arc. Simulations predicted a gentle outward curve, but instead, the object executed a precise lateral drift, a correction just a few kilometers per second. Too small for the average observer to notice, but for mission planners, it was unmistakable. Nothing natural could maintain that kind of controlled deviation. Outgassing might cause random pushes, but never clean, consistent directional change like this. One orbital analyst described it off the record as a maneuver. NASA has not commented publicly on that data. But a few days after the deviation was observed, the James Webb operations team quietly scheduled new observation time under the code name Program 11067B. Normally, observation requests are public, logged in the open archive. This one wasn't. Only the timestamp was visible, with the target field redacted. The astronomical community erupted. On scientific forums, theorists proposed everything from magnetic propulsion to piezoelectric gas jets. One speculative paper even suggested that the object might contain cavities of supercooled carbon dioxide that act as self-venting thrusters when exposed to sunlight, but the periodic precision remained a mystery. How could natural pressure cycles time themselves so exactly, over weeks, without chaos setting in? Then came a discovery that changed the conversation entirely. Buried in archived data from the Chandra X-ray Observatory, astrophysicists found faint X-ray emissions originating from the same coordinates as 3I/Atlas. X-ray radiation isn't typical for comets. It usually requires highly charged particles interacting with gas, producing fluorescent emissions. But the X-rays detected were too focused, too monochromatic, a single narrow band centered at 0.53 kilo-electron volts, the exact energy signature of oxygen ions under artificial excitation. It suggested that something inside the object was producing a steady directed energy release, invisible in optical wavelengths but visible in high-energy spectra. Within days, the story leaked. Not from NASA, but from an independent researcher in Italy who posted an analysis of the Chandra data to an open-access archive. Within hours, the post vanished, taken down under a copyright claim. But copies circulated anyway, fueling speculation that Webb and Chandra had detected something extraordinary, something that wasn't supposed to be public yet. As more amateur telescopes caught glimpses of 3I/Atlas, another strange pattern emerged. The object's brightness curve was modulating not randomly, but with a rhythm almost too deliberate. When brightness changes were converted into audio frequency, astronomers noticed a repeating sequence, 3 pulses, a pause, then 2 more. Over and over. At first it seemed like coincidence, a trick of data compression or solar interference. But it persisted night after night, perfectly consistent, perfectly timed. Some researchers called it natural resonance, the beating of overlapping emission cycles. Others weren't so sure. One of Webb's data engineers anonymously told a journalist that when they plotted the brightness fluctuations over time, the sequence formed geometric ratios, patterns eerily similar to those found in orbital harmonics and musical scales. Coincidence, maybe. But to those who've spent their lives studying randomness in nature, it didn't look random. Behind the curtain, multiple space agencies began coordinating tracking efforts. Though no one said it publicly, there was concern that 3I/Atlas might pass close enough to be influenced by Earth's gravity field. Orbital projections showed it would skim the outer solar system and then swing back outward, but now that it had shown signs of active control, all bets were off. If it adjusted course even slightly, no one could predict where it might go. Through it all, the James Webb Telescope continued to monitor. Deep in its cryogenic stillness, floating at L2, it kept collecting data, frame by frame, wavelength by wavelength. And in that data, scientists noticed something subtle but profound. The object's albedo, its reflectivity, was oscillating in perfect phase with its energy emissions. That means the brightness wasn't just changing randomly, it was breathing. The object was pulsing with a steady rhythm like a heart made of ice and light. No one can yet explain why. Maybe it's a new class of interstellar object, one forged under conditions we've never imagined. Maybe it's a natural mechanism from the chaos of alien chemistry. Or maybe, and this is the thought no one dares to write in an official paper, maybe it's a relic, something ancient, crossing the stars built by hands or forces long gone, still drifting under the laws of physics we only half understand. And as 3I/Atlas fades again into the outer darkness, Webb's instruments remain fixed on its path, waiting, recording. Because somewhere in those numbers, buried among billions of data points, might be the first evidence that the universe has already visited us, not once, but twice, and perhaps many times before. And if what Webb saw is even half true, then we're not the observers anymore. We're the observed.